Let's look at two limit examples with piecewise defined functions. For our first example, we'll let f of x be equal to x if x is less than or equal to 0, x squared if x is greater than 0, and we'll investigate the limit as x goes to 0 of f of x. Before we get started, let me remind you that there was a previous pincast that reviewed the idea of piecewise defined functions, what their graphs look like, how you evaluate a function, etc. So you might be interested in viewing that review pincast if you have forgotten some of those details. But again, back to our problem, let's investigate the limit of this function as x goes to 0. First of all, whenever we want to find the limit as x goes to 0 of a function, we use in this case, 0 plus alpha, since x is going to 0. So x is 0 plus alpha. That means we need to find f of 0 plus alpha, which is the same as f of alpha. But the problem is, if you look back up at the definition of our function, the value of our function at alpha depends on whether alpha is positive, in which case we use the rule f of x is x squared, or negative, in which case we use the rule f of x is equal to x. So again, the value here depends on whether alpha is positive or alpha is negative, and you'll recall that alpha is an arbitrary infinitesimal that might be either positive or negative. But we've also seen this scenario before. When our value of alpha, whether it's positive or negative, matters, the idea we've seen before is to use one-sided limits. And that's what we'll do here. So we'll look separately at the limit as x goes to 0 from the right of f of x and the limit as x goes to 0 from the left of f of x to see what those might be. Now again, here we plug in f of 0 plus omega for limit as x goes to 0 from the right, and it would be f of 0 minus omega for the limit as x goes to 0 from the left. Okay, so in the first one we have f of omega, but because this is a positive value, that means we use the rule for f of x is x squared. So that gives us omega squared, which is approximately 0. Now in the next one, in the limit from the left, f of 0 minus omega, that's the same thing as f of minus omega. But minus omega then is negative. So since that's negative, we use the rule for f of x less than 0. So we use the rule f of x is equal to x. So that would mean we get minus omega, which is also approximately 0. Now recall that the two-sided limit as x goes to 0 of our function, exists if and only if the two-sided, or both of the one-sided limits exist and are the same number. So since both of the one-sided limits are 0, our two-sided limit is 0, and we are done. So that would be our answer in this case. Now, let's look at a graph of that function to remind ourselves of what it looks like so we'll know what we are facing here with our piecewise defined function. Again, if x is less than or equal to 0, we have the graph of y equal x, which you'll recall would be that line. Now, I'll go ahead and fill in the circle since it was x less than or equal to 0. X equals 0 was included. Now, when x is greater than 0, I've got the graph of y equal x squared. So that's what our function looks like. It looks almost like the ones where we had a hole in the graph. It's just the holes filled in. So same idea here of that limit being equal to 0. Okay, let's take a look at example 2. So in example 2, f of x is defined as x plus 1 if x is less than 2, 11 if x is equal to 2, and x squared if x is greater than 2. And this time we want to investigate the limit as x goes to 2 of our function. Well, we'll go straight to the one-sided limits here. We'll look at the limit as x goes to 2 from the right of our function. And we'll look at the limit as x goes to 2 from the left of our function, with the idea that if the two limits are the same, our two-sided limit exists and is that value. So, for limit as x goes to 2 from the right of f of x, we need f of 2 plus omega. But notice that 2 plus omega is bigger than 2, so I use the rule f of x is equal to x squared. So that will give me 2 plus omega squared, which is 4 plus 4 omega plus little omega squared, which is, of course, approximately 4. For limit as x goes to 2 from the left of my function f, I have f of 2 minus omega, and 2 minus omega is less than 2, so that means I use my rule f of x is equal to x plus 1, since x is less than 2. So I've got my 2 minus omega plus 1. That's 3 minus omega, which is approximately 3. Now notice in this case, unlike example 1, our two one-sided limits are not the same. Thus, the limit as x goes to 2, my two-sided limit of my function, does not exist. Now, a quick look at the graph here shows the idea of what's going on. If I go by 4s here on the vertical axis, then I know that when I'm coming from the right, I'm at x squared, and then I have a limit of 4. But when I'm coming from the left, I'm at x plus 1, and so I wind up with a limit of 3. But at 2, the value of my function is 11. So again, this is where we have that jump, or that gap, between our two one-sided limits. But notice this extra point up here, this value up here, that f of 2 is equal to 11. It turns out that that value is irrelevant. Why? We never have to use the rule for x equals 2, because if I'm taking a limit as x goes to 2 from the right or from the left, I'm using a 2 plus omega or a 2 minus omega. I just need to know what's happening when I'm greater than 2 or less than 2. So again, the value there is irrelevant. And when you look at the definition of limit, you'll see that same idea. So this is a very important conclusion to this pencast, that when finding the limit as x goes to b of f of x, the value f of b, if it exists, if it's defined, is completely irrelevant. We don't care what that value is. Again, the reason is, according to the definition, we're finding f of b plus alpha, and so the number we're putting in here, b plus alpha, is not the same as b. So we don't care what it is at b. Okay, so this summarizes then again the idea of finding limits when you have piecewise defined functions.